Good day. I am Jeff F. Galisanao and we are going to present our design experiment in ECE 309, Communications 3, Transmission Media and Antenna Systems and Design, entitled Design of Elliptical Microstrip Patch Antenna with Coaxial Probe Feeding for Satellite Applications using MATLAB. In this presentation, you will learn about the innovative elliptical microstrip patch MSPA antenna and a lot more that will be further discussed and presented by my group mates. The objectives of this study are to design an elliptical microstrip antenna using MATLAB and simulate at 2.35, 2.4, 2.45, and 2.5 gigahertz operating frequency, and FR4 substrate dielectric material, which has 4.2, 4.4, 4.6, and 4.8 dielectric constants. And by the end of this activity, the student shall be able to perform manual computation acquiring the values of wavelength, bandwidth, and percent bandwidth, and simulate a MATLAB code to implement calculations in designing elliptical microstrip antenna, and create a MATLAB program to design an elliptical microstrip patch antenna with varying operating frequencies.
For the discussion, this elliptical microstrip patch antenna uses coaxial probe feeding to present, design, and simulate at ISM band, or Industrial, Scientific, and Medical Frequency Band, in which the standard ISM frequency band ranges from 2.4 GHz to 2.5 GHz. This proposed antenna is specifically designed for satellite applications, so wider bandwidth and excellent gain are expected. Next is the feeding method. The feeding method used is the coaxial probe feeding to excite to radiate the contact. It has two it has two materials which are inner and outer material. The inner material is a conductor and the outer material is for insulating. And lastly, the antenna toolbox by MATLAB. We use this toolbox to make the elliptical microstrip patch antenna possible, since it provides designs and visualizations of the antenna. For the resources, it is required to use a computer station with MATLAB R2013 version or a higher version.
For the procedure and simulation, on our first activity, we compute the values of wavelength in terms of different operating frequencies, which are 2.35, 2.4, 2.45, and 2.5 GHz. We also implement and verify the calculations of procedure 1 using MATLAB. To show you the implementation commands using MATLAB, here are the sample. We also compute the values of bandwidth and percent bandwidth using the obtained frequency from the S-parameter plot of each operating frequency at -10 decibel. For the activity 2, we design an elliptical microstrip antenna that will work with 2.35, 2.4, 2.45, and 2.5 GHz operating frequency. We follow the step-by-step procedure provided and vary the frequency and the electric constant based on the required data. I will show you the simulation of microstrip antenna at 2.35 GHz. This simulation shows how an microstrip elliptical antenna looks like, and also it shows the S-parameter plot, the impedance plot, the 3D radiation path, the gain plot, the BSWR plot, and lastly the beam width. And for further explanation of the data and result, my group mates will present the data and result.
For the data and results, we did some manual computations after simulating the designed microstrip patch antenna to verify the values of different parameters that we got from the MATLAB. So, the wavelength was computed in the activity 1.1. The formula that we have used is C over F is speed of light over frequency, where C equals 3 times 10 raised to 8 meters per second. Next, for the activity 1.2, attached here are the screenshots of the MATLAB implementation. You can see from the figures the commands that we have used in solving for the wavelength. Next, for the data and results of activity 1.3, we computed for the bandwidth of the antenna from different operating frequency. So the first step is to get for the lower and upper cutoff frequency. We can get it from the plot of the S parameter that we have obtained in the MATLAB. Point your cursor on the negative 10 dB, and from there, you'll be able to get the lower and upper cutoff frequency. And to solve for the bandwidth, subtract the upper cutoff frequency to lower cutoff frequency. We also computed for the percent bandwidth of the antenna. The formula that we have used is upper cutoff frequency minus the lower cutoff frequency divided by the operating frequency of the antenna times 100. As a result, the generated commands and functions through MATLAB were equivalent to the results obtained in manual computations.
So for the data and results for activity 2, based on the figure shown, the elliptical microstrip patch antenna is designed and simulated with a different operating frequency at a specific FR4 substrate, such as 2.35 GHz at 4.8, 2.4 GHz at 4.6, 2.45 GHz at 4.4, and 2.5 GHz at 4.2. The antenna design has a wider bandwidth and high gain. So for the S parameters of the antenna, the dielectric or relative permittivity increases as the parameter S11 value has a low reflection coefficient. And for the VSWR, all the values obtained are under 2, which are suitable for antenna applications. For the beam width, it has a 1 to 360 degrees azimuth angle, 0 degrees elevation angle, and a 3 decibel down on the XY plane. The narrower the bandwidth, the higher the gain value. For the impedance and the current distribution, the impedance is the highest where the current is lowest and vice versa. So for the 3D radiation pattern, the proposed antenna has shown a high gain value for all designated frequencies and substrate values. For the azimuth and elevation pattern, these planes these these plane patterns are obtained by slicing the 3D design. The azimuth is taken by cutting through the X to Z plane, and elevation is slicing through the Y to Z plane. So, to sum it up, we provided a table where we acquired results that we needed using MATLAB. So, for the operating frequency of 2.5 gigahertz at 4.2, the S parameter in dB is negative 15.976, VSWR is 1.378, bandwidth in megahertz is 110, percent in bandwidth is 4.4%, beam width is 129, gain in dBi is 5.3. In 2.45 gigahertz at 4.4, the S parameter in dB is negative 16.911, VSWR is 1.333, bandwidth in megahertz is 111, percent in bandwidth is 4.531%, beam width is 128, and gain in dBi is 5.07. For the 2.4 gigahertz at 4.6, the S parameters in dB is 18.282, VSWR is 1.27, bandwidth in megahertz is 111, percent in bandwidth is 4.625%, beam width is at 128, and gain in dBi is 4.92. So lastly, for the 2.35 gigahertz at 4.8, the S parameter in dB is negative 20.589, the VSWR is 1.206, bandwidth in megahertz is 112, percent in bandwidth is 4.766%, beam width is 126, and gain in dBi is 4.82.
For the conclusion, through the help of the reference of this project, we were able to design an elliptical microstrip patch antenna using MATLAB. The designed antenna has a varying operating frequencies of 2.35 GHz, 2.4 GHz, 2.45 GHz, and 2.5 GHz with corresponding FR for substrate dielectric materials having a constant of 4.2, 4.4, 4.6, and 4.8. We have successfully implemented the MATLAB commands that will present the characteristics and parameters of this antenna. Based on the obtained outputs, this antenna has an excellent gain value and bandwidth range. Thus, the designed elliptical microstrip patch antenna has the capability of being used for satellite applications and high-performance systems such as rockets, missiles, and ships. Further, this antenna has exact dimensions that act as a circular polarized wave radiators. With that, I conclude this presentation. Thank you.